considered to be one of the best theoretical physicists who ever lived. Maxwell was also Einstein's hero. He took all the ideas that Faraday came up with, and he was able to express them in the form of mathematics, and some of which we have already seen. Take a look at the first one. Remember the Gauss's law? All right, so Gauss is the guy who came up with the mathematics of it. The electric field within the Gaussian region is going to be created by the charge within. All right, so there's no net magnetic charge within, so this gives you the magnetic field inside its Gaussian region. So we can really focus on this that much, but it's an extension of the Gauss's law. Here's the Faraday's law expressed in the form of mathematics that Maxwell came up with. If you change the flux within a certain region, it's going to cause a circulating electric field. All right, and here's an expression from Ampere. The current causes a circulating magnetic field. Just about the only contribution that Maxwell came up with that gives us the electromagnetic waves is this expression. These are known as Maxwell's equations, but in reality, Maxwell's only contribution is this section of. All right, so simply put, it says if you vary the electric flux within a certain region, it's going to cause a circulating magnetic field within that region. All right, so this is exactly what Faraday was talking about in terms of creation of the electromagnetic waves. So what do I mean by it? Just changing the flux, electric flux within a certain region is going to cause a circulating magnetic field. All right, so that becomes important because of the way Faraday was thinking about it. All right, so he sets out the problem, and we will do this formally later on. I want you to notice two terms here. All right, we talked about epsilon naught. I said, what do you think that is? And then I kind of mumbled something about, hey, he puts the brakes on in terms of how fast the electric field can actually travel in a vacuum. And mu naught does the same thing for the magnetic field component. Evidently, these two things will multiply together and invert it after taking the square root of it is going to give you the light speed. So this is what Maxwell ended up discovering. Maxwell discovered that all electromagnetic waves, in essence, travel at the light speed. Light travels at the light speed. Therefore, light is an electromagnetic wave, just the way Faraday had been talking about it forever. And then he publishes this paper in 1865. 1865, that's like 160 years ago. All right, so I have a few questions for you to answer. All right, they will have a short little debate regarding the questions. Question number one is light travels at the light speed, right? And which also means that the light is an electromagnetic wave, so that's the transverse wave that you're looking at. All right, so question number one. If light is a wave, what is the medium that it's disturbing? Okay, so you have to get back to the definition of a wave, guys. Definition of a wave is a traveling disturbance that carries energy with it, right? So we certainly have a disturbance that's traveling at the light speed. And it's got to be carrying energy, so that's an obvious fact. But how fast the wave travels depends on the medium that it disturbs, right? So what is the medium that the light disturbs so that it can travel at the light speed in a vacuum?
Space.
Okay, so Ian says space. All right, so let's talk about space, empty vacuum of space. What is it that the light is disturbing within the emptiness of a vacuum of space that allows it to go at the light speed? All right, so okay, who said that?
I did.
Okay, so Nathan, what is the medium that the light is disturbing so that it can travel at the light speed? All right, so when I'm talking about a medium, remember we were looking at mechanical waves? And the medium that the mechanical waves are disturbing is the sort of medium which was made up of atoms and molecules, right? So how fast the wave travels depends on the medium itself. And you know, it's going to be the tension, molecular tension between the molecules or the atoms. Higher the tension, as faster they would move. Also the molecular density. As smaller the density was, the faster the wave was supposed to move. But when you look at space itself, it's a vacuum. It's devoid of molecules, right? You got hydrogen molecules. I don't know, one molecule every 100 miles or so, even maybe less. I'm just pulling stuff out of my ass right now, so I don't know what the numbers are. But by and large, the space it's a vacuum. That's what we got. And there's absolutely no molecular tension within space. And then you got this light, which is proposed to be a wave. And the first thing about a wave is a traveling disturbance, and how fast it travels depends on the medium itself. And all of a sudden you look around and there's no medium that it can disturb. How's that possible? All right, I'm just gonna let that question sink in briefly. And the next question that I'm gonna ask is gonna be even more stranger than the first one. All right, go take a 10-minute break.
We have lectures in half an hour.
Well, let me think. Professor Weber and his life-draining monologue, or you, Mozart, and James Clerk Maxwell.
We can't. We'll get a warning.
Our project is too precious to waste time listening to those dullards. Come with me. We'll read Maxwell and think about the electromagnetic theory of light.
Oh.
Wow, this is a dirty talking.
Why, my dear little
In physics.
Johnny, how you enchant a lady. She's very pretty.
Yes. But can she soar and dance like our dark souls do?
Maxwell's equations contained an incredible prediction. They said you could never catch up to a beam of light. Even if you were traveling at 670 million miles an hour, you would still see light squiggle away from you at 670 million miles an hour.
You see how she says it that way?
Yes?
You see how for her it is static?
Yes?
She and the wave are traveling at the same speed. We see the wave moving through the water, but relative to her, it just sits there. So is light like that?
Common sense would say that if you cut up to a light beam, there would be a wave of light just sitting there. Maybe it would be shimmering, a bit of electricity and a bit of magnetism.
So if she was traveling alongside the light wave, it wouldn't be moving. It would be static. But Maxwell says you can't have static light.
Maybe Maxwell is wrong. Maybe if you catch up to light, it is static, Albert, like a wave next to a boat.
Imagine if I was sitting still and holding a mirror to my face. And the light travels from my face to the mirror, and I see my face.
Yes?
However, if I and the mirror were traveling at the speed of light...
You're going at the same speed as the light leaving your face.
Exactly.
The light never reaches the mirror.
So would I be invisible?
That doesn't make sense.
Young Einstein was starting to realize that light was unlike any other kind of wave. Einstein was about to enter a surreal universe where energy, mass, and the speed of light intermingled in a way no one had ever suspected.
All right, so that's going to be the last thing we will discuss before the summer session is over. All right, let's get back to the electromagnetic waves. The lowest frequency region is the highest wavelength region, or the radio wave region. They're generated by using AC circuits. If you can get the current to move up and down between these two numbers inside a wire, 10,000 to 100 million times per second, cycles per second, that range is known as the radio wave region. I pick out the best answer.
C.
All right, you can give yourself 5 points for that one. All right, so the AC circuits, which means that you're pushing the electrons up and down inside a wire at extremely very high frequencies. When we say high frequencies, it's going to be 10,000 to 100 million cycles per second. All right, so radio wave region. Take a look at the loop antenna. They used to have these kind of antennas on top of the TVs. Obviously, today we got cable. So those of you guys, if you still remember these antennas, notice that they're designed to intercept the magnetic field component. So the magnetic field going through the antenna, the area inside the loop would generate an alternating current. And then you have the electronics that's going to decode the information for you. Versus the regular antennas that we use, the car antennas or whatnot. Notice that these are vertical. They are designed to intercept the electric field component. You got the radio waves coming in. So they will, acting on the conduction electrons inside the wire, they will just drive the charges up and down, creating an alternating current. An alternating current, whatever the information is, you got the electrons that's going to decode the information for it. All right, so you can listen to your radio station. Notice that the electric field component is vertical. The antenna is also vertical. All right, so pick out the best answer. So whenever you're ready, jump in.
Vertical.
It's going to be vertical. Give yourself 5 points. Those of you guys who pick vertical, give yourselves 2 points. All right. Electric field component is vertical. Antenna has to be vertical in order to actually intercept the electric field component. All right. So B is the best answer. Microwaves. They're higher than the radio waves. The region is 100 million to a trillion cycles per second. Instead of using wires, we use vacuum tubes with electrons in them. The only thing you have to do is just jiggle the electrons up and down within that region. All right, so, and that's going to give you the microwave region. Once again, it's 100 million to a trillion cycles per second. The main application of microwaves in daily life used to be the microwave ovens.
Let's take a moment to find out how microwaves actually work. A microwave oven uses radio waves to cook food. A device called a magnetron bombards the inside of the oven with radio waves, which react with water molecules in the food, causing them to vibrate at enormous speed. That friction creates heat, which cooks the food.
The Amana radar range microwave oven is quality.
In the early days, it was hailed as a revolutionary kitchen convenience.
The family-sized turkey. 675 watts of cooking power means faster cooking than most other microwave ovens. Uses 50 to 75% less energy than a conventional electric range. 5 and 30-minute timers with automatic defrost cycles.
This store has been selling microwaves ever since those heady times.
Is this the soul of the microwave oven?
More the heart of the microwave. This is a little radio transmitter, and you plug it in, and it converts it to DC voltage, and out comes the microwave.
All right, the Mythbusters
Let's take a moment to
is
find out
absolutely one of my
how
favorites
microwaves
for the wrong reasons and the right reasons. Okay, let's focus on the wrong reasons.
actually work. A microwave oven uses radio waves to cook food.
Really? Do they use radio waves or microwaves? If they use radio waves, I wonder what station they're tuned to. Why not just turn it on and stick your head in it?
A device called a magnetron bombards the inside of the oven with radio waves,
Microwaves.
which react with water molecules in the food, causing them to vibrate at enormous speed.
Not true.
That friction creates heat,
Friction doesn't mean anything in the atomic scale.
which cooks the food.
Cool.
Yeah.
All right, so they just completely missed that one. All right, so what goes on inside the microwave oven that causes cooking? Let's focus on that one. What's going on? Okay, guys, what's happening to the electric field component? Electric field component is going up and down, roughly about 100 million to a trillion times per second. A lot of the cooking happens near a trillion seconds per second. All right, and a lot of the cooking is going to happen whenever the electric field component goes through water or anything which is polar. So notice that you got the positive and negative charges. Electric field is going to grab the positive charge. And then when the electric field changes direction, what happens to the water molecule? All right, so you got the positive and negative charges. Electric field starts to go through it. So it's going to start to spin the water molecule. All right, so if the electric field goes up and down a trillion times per second, this is positive charge. It's going to be up here, and then it becomes here, and then it becomes here. So this thing's going to start to spin. So what happens to the surrounding molecules? All right, this section is completely made up. Imagine that this is your meat molecule. This is your ice cream molecule. All right, so these are polar. These are neutral molecules. So what happens? This becomes polarized. All right, notice that this negative charge, this is going to become positive charge. When this becomes positive charge, this is going to become negative charge. So these molecules will start to vibrate. Random vibrational rotational motion of these molecules is known as heat. All right, so it generates heat. All right, so pick out the best answer.
A.
Hey.
Okay, so just about every single person who says something, you end up saying A. Why not say B? What's wrong with B?
Because the waves don't directly interact with the non-polar molecules.
Okay, very good. Those of you guys who pick A, give yourselves 5 points. Also, I'm going to give you additional 5 points. The waves directly interfere with the polar molecules, and then what happens is the waves will spin the polar molecules. Water molecules have a natural frequency, which is about 1 trillion cycles per second. So when you match that natural frequency, you cause resonance. All right, so which means that you can start feeding energy into it, which means that it's going to start to spin faster and faster. All right, so only about 1 trillion cycles per second. That's the region for cooking. Having said that, cooking inside microwave ovens. Does it happen from inside out or outside in? Okay, guys, just make up your minds at this point. You don't need to say anything. 50% of you guys will say outside in, and the remainder will say inside out. So if you're right, you're just simply going to give yourselves 5 points.